Hello friends, welcome to the ATC Double Cut. My name is Micah Woods, and in today's episode, I am pleased to share a turf hack with you. This is a turf hack that I learned about from Bill Kreuser. And Bill Kreuser, as you know, is a golf course superintendent and also the founder of the Greenkeeper app. And he shared something a couple years ago that I had really struggled with. I couldn't really figure out how to express the amount of water that grass uses or the change in soil water content that is expected for a certain amount of grass water use at the surface, or the change in soil water content to expect with a certain amount of water added to the surface. I couldn't figure out how to do that in US standard units. Now, with metric units, it is a piece of cake, but I'd been doing the metric units for so long, and I just kind of do the metric units intuitively and without really thinking about it, that I just didn't know how to apply that when you're dealing with inches or with the units that are not in liters and millimeters and so on, the metric units that I'm more familiar with. This turf hack was pretty cool, and I think a few other people were surprised at how easy it was. I was surprised at how easy it was. So I'm going to put a direct link to this post with the title Soil Water Content Turf Hacks. I'm going to put a direct link to this post in the show notes and in the video description. And I'm going to explain how this works. And then at the end of this episode, I'm going to explain how I typically do it in metric. So whether you're working with metric units or whether you're working with inches, you will be able to figure out in your head really easily what a certain amount of evapotranspiration is expected to do in terms of changing the soil water content, what a certain water content in the soil is in terms of the amount of depth of water, which is how we think of irrigation, or precipitation. You'll be able to convert between water, precipitation, and amount of water in the soil or changes in water in the soil. So it's really useful to be able to do all of this stuff without having to think about it too much. And the metric way is how I've been doing it for many, many years. And then I learned from Bill Kreuser how to do it in inches also. I started off this post by writing an easy way to relate inches of irrigation or inches of evapotranspiration to changes in volumetric soil water content. That is something I could never figure out. I was thrilled to see the calculations shared by Bill Kreuser. It turns out this is incredibly simple. Now, just a little bit of background information. Evapotranspiration is the combination of the water evaporated from a surface and transpired by the plants. And for actively growing turf grass or for irrigated turf grass, that is typically going to be primarily transpiration, because you don't get so much evaporation from the surface when it's covered by turf grass. So that's mostly the water that's transpired by the grass. And then volumetric water content, that is VWC, and that is the percentage number that you often see with soil moisture sensors or in-ground soil moisture sensors. Those are typically expressing the water content on a volumetric basis, meaning 15% VWC or 15% water content means 15% of the soil volume is water. And in metric, it's really easy to figure out how that volume is related to a depth of water at the surface, but I couldn't quite figure out how to do that with inches. And then Bill, in 2021, June 17th of 2021, he sent a tweet that shows exactly how to do it. And it was a particularly high evapotranspiration forecast. He was looking at the forecast evapotranspiration from the National Weather Service in the United States, and they predicted high water use today. They were predicting a forecast reference evapotranspiration of 0.37 inches, and that is a lot. That's going to be something like 7 or 8 millimeters. That's a very high forecast evapotranspiration. The air temperature was going to be 104 degrees Fahrenheit, which is about 38 or 39 degrees Celsius. The relative humidity was going to be 12%, which is really low. The wind was going to be at 15 miles per hour, gusting to 24, and that is above average wind. And then so you combine a high temperature, sunshine, low relative humidity, and high wind, and you get a high forecast evapotranspiration. So Bill wrote in that tweet, he said, with a 10% wilt point, 6-inch deep roots, and an 80% crop coefficient, the greens need to be at about 15% to make it through the day. So what he means by that is the greens needed to be at about 15% at the start of the day, and then they will drop down to the wilting point, or they'll stay just above the wilting point if they have that much evapotranspiration. If you start at above 15% and then you have that much evapotranspiration, then the soil moisture content will stay above the wilting point at the end of the day. So how did he figure that out? And I thought that might be impossible to easily figure out with inches, and it turns out it is ridiculously simple. So his very next tweet, he said, the math, in case you are wondering. Step number 1, multiply the ET by the crop coefficient. So I'm going to explain what is happening here and what these numbers really mean. So we've got a forecast evapotranspiration that was 0.37 inches, and that means that the reference evapotranspiration is expected to be about 0.37 inches. That's the amount of water that is expected to be used with those weather conditions in the upcoming day. For turfgrass, we typically are going to use some type of crop coefficient, and we multiply the crop coefficient times the reference evapotranspiration to get the crop evapotranspiration. For cool season grass, which Bill is growing at the Jim Ager golf course, it is common to use a crop coefficient of 0.8 or 80%. So if you multiply 0.37 inches times a crop coefficient of 0.8 or a crop coefficient of 80%, you get 0.3. So what that does is takes your reference evapotranspiration and adjusts it to the crop that you're growing to say, for that type of reference evapotranspiration adjusted to the crop that we are growing, we're going to expect that our crop will use this amount of water. So in this case, you've adjusted your reference evapotranspiration of 0.37 to your crop evapotranspiration of 0.3. And you do that by multiplying it times the crop coefficient. If you don't know what crop coefficient you should use, it's standard for cool season grasses to use a crop coefficient of 0.8, and it is standard for warm season grasses to use a crop coefficient of 0.6. And there are other adjustments that can be made about crop coefficients, and I'm not going to go into them here, but just as a starting point, those are the numbers that I think it makes sense to use. So that's a crude way of taking your reference evapotranspiration and adjusting it to something that's going to work for your crop. So in cool season grass multiplied by 0.8, that takes us down to 0.3. So that's the number. We're expecting that the soil would be depleted by 0.3 inches if the grass uses that over the day, because the evapotranspiration is the expected water use, and we're expecting that to be 0.3. I hope that makes sense. So that's step one. Multiply the ET by the crop coefficient. And then the second step that Bill gives, he said, divide that value by the rooting depth. Now, this is the part that makes it all work. And this is the part that I had not realized it was so easy. If you take a depth of water and divide it by a depth of rooting, you now have your volumetric percentage. And it's actually that simple. And that's the part that had completely eluded me. And I never realized that you could do this because it was so easy for me to do this in metric. I didn't really even think about it. But if you take 0.3 and your rooting depth is 6 inches, then that is a value of 0.05 or 5%. So you've got your expected water use for that day is 0.3 inches. And if your rooting depth is 6 inches, then that is 5%. 0.3 is 5% of 6 inches. And in this episode, rather than trying to do all of this in my head and then say, oh, I should have had a calculator handy, or I should have worked out this calculation to be certain that it's correct, I conveniently knew what I was going to be talking about. And I put this in my notebook and I calculated it in advance. So yeah, that is correct. 0.3 divided by 6 inches is 0.05 or 5%. So what that means is we now know that the soil water content we would expect it at a depth of 6 inches at a root zone depth of 6 inches to change by 5% if you take away 0.3 inches. We would also expect it to go up by 5% if you would add 0.3 inches of water. So that it's very useful to be able to do that and to very quickly make those kind of calculations. So step 3 is to add that value to the wilt point or the end of day goal. So in this case, Bill has said that for his greens, the wilting point, or for his turf, the wilting point is 10%. He's using a value of 10% for the wilt point. When you use a value of 10% for the wilt point, and then you know that the grass would be using 5% water over the course of the day, if that's the ET, then you just add that 5% to the wilting point of 10%, and you know that the greens would need to be at 15% or higher soil water content at the start of the day to make it through a day that has the ET of 0.3 inches. It's that simple, and that is a really cool turf hack related to irrigation and soil water content. So I wrote in the blog post, take the depth of water added or lost and divide by the depth of the root zone, and you are now in units of volumetric water content. It's that simple, and doing this provides a straightforward way to convert between units of soil volumetric water content and evapotranspiration and irrigation amounts. So that is something that I have always done in metric, and I put a line in the blog post, and then I said I've been using a different hack for this, which I find even easier, and I went on to explain it. And I will explain it here real quickly for those of you who are interested, or for those of you who actually do use metric units. I generally use a root zone depth of 10 centimeters, which is 4 inches. I find this convenient because 1 square meter to a depth of 10 centimeters has 100 liters of volume. I find that useful for mental math purposes, and I also find it realistic for what we can expect for a turfgrass root zone where the grass is mowed relatively short. Most of the roots will tend to be in the top 10 centimeters. So it's realistic for a root zone. And also, we can expect that most of the plant's water use, most of the plant's everything is happening from the top of the root zone anyway. There's something that is a rule of thumb, a 40, 30, 20, 10, where if you divide a root zone of any depth into quarters, so you've got the top 25% of the root zone, then you've got the second 25% and the third 25%, and at the very bottom, you'd have the fourth 25%. You can expect that 40% of the water uptake would happen from the top 25% and 30% would happen from the second 25%. So already we've got 40 plus 30 equals 70%. We can expect 70% of the water uptake would be happening from the top 50% of the root zone, of the root zone's depth. And then it goes down to 20%. 20% would be coming from the third quarter of the root zone in depth, and only 10% is happening at the very bottom of the root zone, at the lowest 25% of the root zone. So that's 40, 30, 20, 10. It adds to 100%. I don't know that we need to assume that it's exactly like that, and I think it would be difficult to prove that it's exactly like that, but it is something like that. You can expect that there are more roots closer to the surface, certainly more live and active roots closer to the surface than there are deeper in the root zone. And you can expect that your nutrient uptake happens like that. You can expect that your water uptake happens like that. 40, 30, 20, 10. So because of that, even if we do have a deeper root zone, I still think it makes sense to use a 10 centimeter depth root zone for these types of calculations, because most of the nutrient uptake and the water uptake is happening in that top 10 centimeters anyway. So if we do that, it's very convenient to know that we have a 100 liter volume of root zone and 1 millimeter of water at the surface is 1 liter of water. So 1 liter of water spread on the surface of 1 square meter going into a volume of soil that is 100 liters of volume will change it by 1%. So 1 millimeter of water changes it by 1%. 1 millimeter of evapotranspiration or 1 millimeter of plant water use also changes the soil water content by 1%. And that, for me, is just so simple to do that in metric that I didn't realize that if you simply divide in inches the depth of water by the depth of your root zone, you also instantly get percentage, and now you instantly are dealing with the volumetric water content. So it's really good to know that. And I think if you are a professional turfgrass manager, whether you're doing metric or whether you're doing US standard units, you really want to know how much water you're using, how much water's in the soil, how much it depletes over the course of a day. And it's useful. I find it useful to check what your ET is, which ET is a calculated value. It's not, I generally am using ET to refer to a calculated value. And we talk maybe about consumptive water use or change in the soil water content. That's actually what's happened in terms of plant water use. It's useful to compare those two, and from that you can get some idea of what your crop coefficient should be for the way that you want your turf to be maintained. So it starts off by looking at how much your soil water content changes from the start of the day to the end of the day, and comparing that to what the ET was. So that's why I like to know this, and I like to know if my soil water content is 15% right now, and if I want to add enough irrigation to make it 22%, then I would like to know how much water to add. That is a piece of cake when you're using metric, because I know instantly the difference is 7%, so the difference is going to be 7 millimeters. So I need to add 7 millimeters of water to change it like that, because I'm using my little hack of having a 100 liter volume root zone. But now I know that it is relatively easy to figure that out in inches also, and that is yeah, I mean, maybe y'all know that already. You should. I mean, I should have known that. It's so easy. You would just take the depth of your root zone. So let's say we have a 6-inch deep root zone, and you'd multiply that times 7%, and that's going to give you the depth of water that's necessary to change it by 7%. So that's pretty simple. It's useful, and getting the amount of water supplied to the turf right, getting the right amount of water supplied to the turf is just so important for having the desired type of playability, the desired type of turf grass appearance. In some cases, to just even keep the grass alive, you need to make sure that the soil water content is managed as well as possible. So I think knowing these numbers, this is one of the most important numbers that you can know about turf grass management. And one of the most important numbers that you can know to improve the way that the turf is managed. All right, that is about all I have for this little turf hack. If you like more of this turf grass math type of stuff, I have the idea that we might talk about it some more. I have a few math things that I would like to talk about, and I think I've hinted at doing some of these as a bit of a series. So I wanted to talk about this one now because I think the connection between water added to the surface that then goes into the soil and the volumetric water content is something that's really important to be really, really familiar with. And if you use water by time, if you add 5 minutes of water, 10 minutes of water, or 15 minutes of water, that's not the way I would do it. It doesn't transfer very well, so I would suggest to think of depth, and maybe I will talk about that some more another time. All right, thanks for listening. Thanks for watching. I will sign off now for ATC from Yantakao, Thailand. I am Micah Woods. Bye-bye.